user level and kernel level threads are going to be executed. Okay, so now we have learned in previous chapter there were many mappings, one-to-one mapping, many-to-one mapping, many-to-many mapping. Okay, so you have thread library schedules user level thread to run the lightweight process. So in a single thread you are calling it as a lightweight process. Okay, now this is known as a process contention scope. Okay, so since scheduling computation is within the process, so that means thread, the thread is nothing but like it is like a function, or it may function which is running in parallel with a main program. So that means all these threads are belonging to the same process. Okay, now when these threads are running in parallel to a main program, you are having multiple threads which is running in parallel with the main program. Okay, now all are belonging to your same process. Okay, now when a thread is executing, a thread will be has also to be executed in CPU. Okay, now there's a competition between these threads, okay, or your main code of your program to get the access of your CPU. So this is called as a process contention scope. Okay, so kernel thread, so that process contention scope, so this will come where the scheduling decision has to be taken for the user level threads. So similarly we have system contention scope, so where we are taking a scheduling decisions for kernel level threads. So like this we're going to have P thread, so POSIX thread. So you have application programmer interface allows PCS or SCS during the thread creation. So we have P thread scope process, P thread scope systems, okay, which is we are using Linux system, so you are not aware of this. Okay, but these the commands we are going to use in this. So this is a code, okay, which is used for the thread. So when you actually this you will be learning in system software. Okay, now multiple processor scheduling. So multiple processor scheduling. Now till now we have seen one single ready queue where the scheduler has to take a decision. Then how the scheduler has to take a decision, what criteria it has to look about when you are having a multiple queues. Okay, now when we have multiple processors, okay, so then how does scheduler has to take a decision? So CPU scheduling becomes more complex when you are having multiple CPUs are available. Okay, so one case you are having a homogeneous processor within a multi-processor. That means all the CPUs whatever you are having are of same make. Okay, like you are having Intel, all processors are of Intel. Okay, that is called as a homogeneous processing. So there again the decisions has to be taken. Then asymmetric multiprocessing, where you have a single processor accessing the system data structure, elevating the need of data sharing. So where the single processor is taking a scheduling decision, and that processor is going to access the data structure and all. Okay, now there also your scheduler has to take care how the the entire control of your scheduler will be there with a single CPU. Okay, next is a symmetric multiprocessing. Each processor is self-scheduling. Okay, now all the process you are having multiple CPUs, all are okay, but in this arrangement, okay, so like in asymmetric multiprocessing you have dedicated master and the others are slave. So master is taking a decision. Okay, here there is no symmetric multiprocessing, there is no concept of your master or slave. Each processor will be taking self decision. Okay, now you may have a common ready queue where the process are being picked up from different CPUs. Okay, or else you can have separate ready queues for each process. They are taking a self decision. So your scheduler will be taking a decisions based on the ready queue, whether you are having individual ready queues or the multiple ready queues. So processor affinity, process has affinity for processor on which it is currently running. Soft affinity, hard affinity. So hard affinity says that a process is affiniated to only CPU. That part is like you suppose example you're having CPU 1, CPU 2 and CPU 3. Okay, so one particular process wants to execute, must and should it wants to execute on CPU 1. Okay, so that means it is having affinity to CPU 1. So when there is a hard restriction that it has to be executed on that, so that is called as a hard affinity. Suppose soft affinity, it may be having affinity, but even then if you are going to schedule that to the another CPU, that's also fine. So that is called as a soft affinity. Okay. So NUMA and CPU scheduling. So NUMA, here we are going to speak about how locally the memory is going to be shared in the multiprocessor, and how the scheduling decisions are going to be taken. So we are not going to deep into this. Then multi-core processor, you are having same thing, 2 cores. Okay, for a same CPU you are having multiple cores where the decisions have, and each core is going to execute one particular thread, or it may be executing particular process. Okay, how it is going to execute there. Okay, and then so we are having different operating systems examples. Okay. So you can just go through all this, just a snapshot which is available in your textbooks also. So then we have Linux scheduling. Okay, then algorithm evaluation. How we are going to evaluate algorithm. So one is called as a deterministic modeling. Okay, takes a particular takes a particular predetermined workload and defines the performance of your each algorithm for that workload. Okay, so that means you take a particular workload, okay, and then give that workload to a particular algorithm, and then check out what is the performance, what is the average waiting time and average turnaround time for that particular process. Okay, and then you are giving a particular workload for that particular process, and then check out the performance. Okay, so for the same kind of your problem with the same CPU bus, I'll give the same problem to run out that using a different algorithms, and how check out what will be your waiting time and what will be your turnaround time. And then queuing models. So queuing models actually implement a different queues and check out what is the waiting time each queue is going to be, each queue it is going to take. Okay, so that is called as a queuing model, where we actually implement a queue and then see that, then implementation implement it and then check out the performance of it. Okay.